gratuitous bit of Spark code, although I do notice I've picked something with very few Spark annotations. There you go. Training. So we trained 57 people, mostly contractors and clients, okay, because practice employees have got the skill anyway. Very diverse programming backgrounds, everything from virtually no programming through web programmers through to hardcore embedded and real-time programmers. All of our Spark coders are also Z readers, and we find Spark course is a week, if I remember correctly, and we find pretty much people come off the Spark code as effective immediately. Picking up RTE proof, so again, going back to my definition of fluency of as good as somebody who's been doing it for a year, I reckon it takes about 2 months, okay, before a newly trained Spark engineer is doing RTE proof at the same kind of speed as the long-term ones. Bearing in mind you don't do proof day in, day out, it's one of the activities you do whilst you're developing code, so you maybe spend half an hour on it one day, 2 hours on it the next day, and over a duration of about 2 months people are up to speed. We don't actually do correctness proofs on this project, so we're not formally proving the code is formally correct or partially formally correct against the Z specification. Okay, for the level of integrity of this project, it is not cost effective, okay? Harking back to my initial comments on profit. So we don't have genuine data on how long it would take to pick up doing formal correctness proofs. My feel is that it'll be slightly longer again, so maybe 2.5, 3 months. It is a slightly different skill. In terms of tools, obviously compared to the Z, we've got a very mature and excellent tool set. Again, I'm not going to go into it, but if you want to talk to me afterwards, please do, or see your ADA core rep for a very reasonable quotation. So we'll round out by looking at formal methods as we come back up the test side of the V. Our testing is very much driven by the Z, okay? We actually require specification and code coverage, very driven from the Z specification. We devise possible conditions by analysis using mathematics on the Z specification, equivalence classes, partition analysis, that kind of thing. And we write these down in a very Z-like notation, so you can see on the bottom some very Z-like notation, some bullets to say when items apply. Okay? It's a fairly straightforward activity, a fairly mechanical activity. Once people have been on the Z course, they pick this kind of thing up fairly quickly. Z readers, obviously. The challenge of test and formally derived test conditions is keeping your test program under control. Just because you can generate a test case does not necessarily mean it's a good idea to go to all the effort of writing a test script and running it. Okay? Picked a small piece of Z. That's a fairly normal piece of Z. Okay? If we turn the handle on this, how many test conditions do we get? The answer is far too many. Okay? 1,134 theoretical tests you can generate by applying the mathematics. Okay? It's not a commercially viable proposition to write 1,100 test cases for that piece of Z. Don't forget we've got 4,250 pages, yeah? And that certainly wasn't the page we started with. So, we work through, we remove duplicates, we remove contradictions, we carefully remove low-value test cases. It's an activity that takes skill, okay? It takes domain knowledge to understand what the system is, and what a low-value test case is very much a domain-related issue. It takes judgment, okay, and it takes time. If you take the easy option and go, oh, we'll keep that test in, we'll keep that test in, we'll keep that test in, what you find is that because it's an easy option, you haven't had to make any judgment calls, but you've kept all the tests in, and you're back to a commercially unviable test program that goes out into the middle of next year. Of course, we need to be very careful. Okay, we do need a verification argument at the end of the day. We do need to show specification coverage from our test suite or verification activities. We do need to make sure the system's safe. Okay, so what we do is we triage out what we can, and then we write our test scripts very, very carefully to knock off as many conditions as we possibly can. And in fact, after you've done those activities, if you go through the 1,100, you remove the dead wood, as it were, and you carefully write test scripts. You only need 6 test scripts to cover the remainder, okay? And then you're far more back into a viable world. But it does require judgment, it does require skill, okay? Oops, go right to the bottom. So formal methods are not a substitute for initiative, I reckon. Yeah. So lastly, when we come to testing some of the algorithms are specified in pure mathematics. Okay, working out the expected answers for your test cases can be very, very difficult. Okay? If you do it manually, it's also very error prone. Okay? So what we do is we create a reference implementation, what we call our reference implementation in Mathematica in this sense. So we use diverse people, different team of engineers. We use a diverse tool, Mathematica versus Spark. We build some walls between them. We don't let them talk to each other in case they pass each other useful bits of information. Okay. And then when we want to run our tests, we run them back to back through the real system and through the reference model. And obviously what we do at the end is we compare the answer to make sure they're tolerably close. You do get differences, of course, because Mathematica has a perfect real number representation, whereas Ada's real numbers are a model. So you'll get differences because these are real number algorithms. We have a model of error bounds, so we know what is tolerable. You need to be a bit careful. Obviously the downside of this is when your test fails, you have no idea whether the real system is at fault, or of course whether your reference model is at fault. And it doesn't give you any help in which one you should go and look at. So if you're not careful, you end up investigating twice as many failures. In particular, if your reference model is buggy, yeah, this doesn't help your test program at all, because you get hundreds of failures and no more confidence of whether it's your reference model or your system. Crucially for us, reference model has shown to have a very similar defect density to the Spark implementation. Okay. Roughly, for test failures, roughly the same number have been in the real Spark implementation as the Mathematica reference model. We need to be careful, it's a small team, we've only trained 5 people, is it 5 people doing this? So we don't draw too many conclusions from a small study, but that's where we are. And I would point out the Mathematica course is too slow to use in the real system, the Spark model runs a lot faster. So to conclude, are formal methods applicable across the life cycle? Well, I think yes, they are. We use them in specification, we use them in development, we use them in test. We've got a project of over 100 engineers, 120 engineers, and we've had basically 0 scaling problems in the technologies we've used. In particular, the off-cited barriers or the people present, for example, training, just haven't materialised as barriers for us. Yes, we'd have to train people. Yes, we have to invest 3 days in training everybody on Spark course. But on a 5-year project, 3 days is noise. Okay. It's a one-off cost, of course, and if we use those people on later projects, we don't need to train them again. Our data shows that the training's comparatively cheap and easy, and that success rate from people learning the skills is very, very high. If there is an Achilles heel, it's in tool support. Okay. Talked about the specification tools, which in specification silo are tolerable. Okay. The development tools, obviously the Spark toolset's very good. We have an HMI, some of the HMI is written in C code. The tool support for C code is limited. On the test side, the tool support is virtually non-existent. Okay. Overall, the tool support is there or thereabouts. It's tolerable, but it can certainly do with improving. In terms of integration, Cyril was talking earlier about using a standard notation to enable all these tools to use one notation rather than rewrite it time and time again. That is an area where we really, really need to make some progress. At the moment, we have a bunch of formal tools that are unintegrated. Okay? And you can fall down the gaps between the tools. Okay? Where we really need to make progress is in the tool support for each silo, and then the integrated tool support across the project. And that's about all I was going to say. I'm quite happy to take questions. I know this conference has started a policy of a very small number of questions, all of which are very easy to answer. I'd encourage you to stick with that policy.